Simple linear regression. Regression and correlation are essentially the same mathematically. The product moment correlation between x and y is equal to the beta of x in a simple linear regression line, or y equals alpha plus beta x. So that beta represents the relationship, the association between x and y, and mathematically they're in the same number. The difference between correlation and regression is conceptual. They're conceptual bases. Correlation is conceived as an interdependent association. That is, it's a reflection of the shared variance between two variables. Regression, on the other hand, is conceived as a dependent association. One of the variables is a cause and the other is effect. So one of the value of one variable depends on the other. So with x and y, normally we presume that x is the independent variable and y is the effect. So a model that explains the value of a dependent variable in terms of an independent variable can also be use the terms criterion variable and predictor variable. So this idea that one variable is predicting an effect is part of linear regression. So the aim of linear regression is to construct a straight line, a linear relationship that explains a scatter plot of data. So we can describe this straight line as y equals alpha plus beta x, where alpha is the y-intercept. It's that point where x equals 0, so y, the line becomes y equals alpha. And beta is the slope of the line. So it indicates the extent of the influence between x and y. So you see here a figure with a scatter plot, and the red line through it is the line that best represents the values of those data. Where the line crosses the y-axis is the A or alpha point, and the slope of the line is the B or the beta point. Now we use the term, the English letters A and B when we're talking about raw. Those are called the raw coefficients, and the alpha, beta Greek letters are the standardized coefficients. And these coefficients have different values, but they express exactly the same relationships. The difference is that we use raw coefficients whenever we're using raw data, and we use standardized coefficients whenever we're using standardized variables. And a standardized variable, as we've seen before, is the variable value minus the mean for that variable divided by the standard deviation of that variable. And whether we use raw scores or standardized scores determines what sort of applications we can make. The raw scores use the actual measures from the sample. So for example, if we had the questions, if we had measures of income and housing purchase price, and so we were trying to predict how much people spend on a house from a knowledge of their income, and those raw scores then would be in dollars of income and dollars of price per house. And we could use that relationship to predict the price of a house for any household. So if we had a household that had an income of $226,000 we would be able to use our simple linear regression to predict how much that household would spend on its house. We could not compare that relationship with some other relationship, with the relationship of another variable to income. So let's say we also had a measure of brand attitude toward Mercedes on a 7-point scale. We couldn't use the relationship between, we couldn't compare the raw correlation between income and housing price with the raw correlation between income and attitude toward Mercedes. On the other hand, if we look at the standardized coefficients, we could. So if we standardize those income and housing price coefficients, then what we have is a relationship not between dollars and dollars, but between standard deviations on one variable and standard deviations on another variable. And if we also had standardized the attitude toward Mercedes variable, we'd have a correlation, a standardized coefficient between income and housing price, and a standardized coefficient between income and attitude toward Mercedes, and we could compare those results in a meaningful way. So we could say, oh, the relationship between housing price and income is slightly weaker than the correlation between attitude toward Mercedes and income. And that's clearly not going to be the case with raw coefficients, because the size of the raw coefficient is a function of the size of the instrument that was used to measure. If we measured housing price in thousands of dollars, that would affect the raw coefficient relative to simply using whole dollars. But it wouldn't affect the standardized coefficient. So whether you're using the relationship to predict another outcome or to compare relationships determines whether you want to use the raw coefficients or the standardized coefficients. How do we compute the intercept and correlations for regression? Conceptually, we can think of this as a visual inspection, and in some cases a visual inspection is a reasonable approximation. This is sometimes jokingly referred to as an interocular trauma test. We're essentially putting lines on scattergrams in such a way that the line seems to fit the data. And you should see that the line on the left appears to fit the line less well than the line on the right, the red line. Now, what we mean by that is that the data on the right line the data points appear to be closer to the line. And that's essentially the way regression is done mathematically. We're trying to minimize differences between the data points and the regression line. Now, there are a number of ways to minimize those differences, but the most common is called OLS, or the ordinary least squares approach. For this algorithm, the objective is to minimize the sum of squares of error. So we formulate that visual as the sum of the deviations between the y-score and the predicted y-score. So that y with a little hat over it or caret over it is the estimate of y, the estimate made by the regression line. And again, we're squaring those deviations because there are going to be as many total deviations above as below the line. And the comparison is the mean of y, because if there is no predictor variable, if we don't run a regression, then what we're going to estimate for any x value is y bar, the average of our sample. So the regression line replaces y bar as the estimate, and each point of the line corresponds to an x value, and that corresponding y value will be y hat, the estimate from the regression model. So those terms allow us to talk about the construction of the test statistic for regression, which is an f-test. Now, we've seen the f-test before. It's the same f-test that is used in analysis of variance. And in fact, the model underlying analysis of variance is a regression model. It partitions error. So it says that the total deviation of the line of the individual data point from the best estimator, which is the mean, can be divided into the deviation that's explained by the line and the deviation that's unexplained by the line. So formally, that is the sum of the y sub I, which is the individual data points, minus the y bar, that quantity squared, can be partitioned into the sum of the difference between the estimate and y bar and the difference between the actual point and the estimate. And this reads as the sum of squares total is equal to the sum of squares of the regression plus the sum of the squares of error. And shorthand is SST equals SSR plus SSE. So look at this figure and see an illustration for a value of x out here on the right. There's the corresponding data point, y sub I, the little dot. And our default estimate for y for that value of x and for any value of x would be y bar. So the question is, how much have we improved that estimate by putting in the regression line? Well, the regression line is above y bar. It's somewhat closer to y sub I. So the effect of the regression line is the difference between the regression estimate y hat and y bar. But we don't explain that data point perfectly, so what remains is the difference between y sub I and y hat. So this expression of the partition error, sum of squares total equals sum of squares of the regression and sum of squares of error, can be used for two descriptors of the regression model. The first is the f-test, the test of the statistical significance of the model, and that compares the amount of explanation by the regression with the amount of explanation that remains in error. And you can see that proportion here. It's the sum of squares of regression divided by its degrees of freedom, which is k minus 1. And k is the number of variables in the regression equation, including the intercept. So with simple regression, you've got two variables, so 2 minus 1, 1 degree of freedom. And in the denominator, the sum of squares of error divided by its degrees of freedom, which is n minus k, where n is the number of observation and k is the number of variables. So as the sum of squares due to the regression increases, the value of f goes up. And as the sum of squares of error increases, the value of f goes down. So a higher f observed means it's more likely a statistically significant effect because relatively more of the variance is explained by the regression than is explained by error. A second measure of a regression model comes from another proportion of these partition errors, the sum of squares of regression over the sum of squares total. So you should see this as the proportion of the deviations that's explained by the line. The sum of squares of regression is the explained variance, and the sum of squares total is the total variance. So as that approaches 100%, r squared goes up to 1.0. So an r squared of 1.0 would mean you have perfect explanation that the regression line explains all of the variance, and of course that would be a scatter plot with all the lines perfectly lined up on one linear line. And r squared is in fact the square of r, which is the standardized coefficient for beta, mathematically. So the steps in interpreting a regression analysis are to look at the model, y equals alpha plus beta x, then look at the f-test. Remember that the f-test is an indicator of the significance of the variance explained by the model. So if the f is not statistically significant, that is, if the observed f is not greater than the critical value from a table, then the model is not explaining enough variance to be considered interpretable. So an insignificant f-test is the end of the interpretation. If the model is significant, then one can look at r squared as an indication of how much of the variance is explained. Now this has to be done carefully because there's no cutoff for r squared. In hard science, r squareds are typically quite high, approaching 1.0, but in social sciences, often one will find a significant f statistic for r squares of only a few percentage, which means that only a few percentage points of the variance are being explained by the model. It is, however, useful in making comparisons across models, particularly models that use the same variables at different points in time, or models that share some of the same variables. So often the researcher is trying to pick a model that does better than other models to explain the same phenomena. And finally, one looks at t-tests for individual coefficients. Now, in a simple linear regression, there's only one explanatory variable, so there's only one t-test. And in that simple regression, of course, we would expect to see a perfect correlation between the t-test of the variable and the f-test of the overall model, because that's all the model is an examination of the relationship between those two variables. And in fact, t squared equals f mathematically. Now, when regression analysis is used for hypothesis testing, there are two requirements. First of all, the direction of the coefficient has to be in the predicted direction. So if you expect that, for example, people of higher income to pay more for their houses, then you expect to see a positive sign for either B or beta, either the raw scores or the standardized scores. And if the coefficient has the proper sign, then the model also has to be significant. So to conclude that a regression supports an hypothesis, there must be the appropriate sign on the coefficient, and the model must be significant. In multiple regression, not only must the model be significant, but the t-test for the individual coefficient must be significant.